All right, so look, here's the question. How much energy is required to heat a 10-gram sample of water from 50 degrees C to 120 degrees C? Okay? There are three equations involved here, and the answers to all three of those equations have to be added together. We're starting at 50 degrees C, and 50 degrees C on the heating curve for water is in this range right here. And so we can heat up the water from 50 degrees C. We can't get any hotter than 100 degrees C. Liquid water can't be more than 100 degrees C. So we're going to use this equation right here for a change in temperature. Change in temperature is always temperature final minus temperature initial. The initial temperature, let's start with the final temperature for liquid water can be only up to 100 degrees C. We're heating it up, so we can only go to 100 degrees C. And the initial temperature is what we started at. So we got a 50 degree C change in temperature, okay? All right, the mass is 10.00 grams. Guys, just to be clear, if you want full credit on a problem like this on a test, you've got to show me all this stuff. You have to show me the values. You have to show me the equation that doesn't have any values plugged in. Then show me how you plug in the values. Show me the math. Okay? If you don't put your numbers up here vertically and figure out there's a significant digit here after the decimal place, and you calculate it wrong and your significant digits are wrong, you're going to lose some points. Not only because you don't show this, but because your final answer is not going to have the right number of significant digits. Okay? So put everything down. Don't skimp on the pencil graphite. Okay? So 10 grams. What we need now is the specific heat of water. That is listed in your test references. Let's see. Let me get a copy of that of the type that you guys have. I'm going to print a set out for the test. You won't be using your personal set. You'll be using my set for the test. It's exactly like your personal set, except that it's on yellow paper. Or maybe blue paper. I forget what color paper it is. I'll figure that out tonight. Okay? All right, so here's the specific heat for water. Liquid water right here, CP, 4.18 joules per degree C per gram. Okay? Since this is a fraction and we're multiplying this by a fraction, let's just line everything up in fraction because it kind of makes it easier to figure out what we're going to do to cancel units and such. Okay? And then we got to multiply the change in temperature. We got that over here. Okay? And again, we're putting it over 1 just to make everything line up nice and neat. And then we're going to simplify by canceling out units. Okay, just like x's and y's in algebra, these units of measurement can cancel. So can chemical species. We just don't have any in this kind of problem. So now we're ready to do the math. All right, so 10.00 times, whoops, it's not doing it on the calculator. Why not? 10.00 times 4.18 times 50.0, and we get 2090 joules. We look at all the measured and calculated numbers in the problem. Everything across the top is either measured or calculated in this problem. 4 digits, 3 digits, and 3 digits. So we want to have our final answer have the same number of digits as the measured or calculated number with the least digits up here. So we want 3 digits. That means these 3 digits here are significant and this one is not. So we have to round it off, and we round off a number where we're getting rid of a number or a digit rather in the ones place. Then we've got to write it in scientific notation. We move the decimal place 1, 2, 3 places. So we get 2.09. Okay, and then that's times 10 to the third because we moved the decimal place 3 places to the left. Okay, and that's joules. And so that's our first of 3 answers we have to have the 3 equations which we're going to add together. Now the second one then is where we're changing liquid water into steam. We've got the water up to 100 degrees C. Okay, now we're ready to change it into steam. So looking back at the graph we showed you a moment ago that we filled out everything on earlier, and earlier in the unit. This is the range we're changing into steam right here, okay? And so there's no change in temperature. Temperature we have on this vertical axis, temperature's not going up when we're changing into steam. So we need an equation that doesn't have a change in temperature function. And that equation is mass times change in enthalpy in the system. Okay? Well, the mass doesn't change. It's the same, 10.00 grams. The enthalpy change, again, this is on your test references. Here's the vaporization of water. Okay? That's where we're boiling the water. Right there. Okay? Delta H is 2260 joules per gram. All right? 2260 joules per gram. We're going to put this over 1 to kind of match it up nice and neat. Go to the calculator. And we take 10.00 times 2260, and we get 2260. No, I'm sorry, I didn't put that in right. 10.00 times 22. I know that didn't look right. All right, 22,600. Okay. Probably could have done that in your head. 22,600 joules. How many significant digits do we need? 3. Okay, remember, trailing zeros are significant only if there's a decimal place. I'm not showing a decimal place there, therefore this zero is not going to be significant. So this is 3 significant digits. Okay, we're going to count 1, 2, 3, underline these 2 digits, move our decimal place 1, 2, 3, 4 places, and we get 2.26 times 10 to the 4th joules. Okay? Now we need an equation where we can change the temperature. We're back to a range here where we can change the temperature of the substance. We can change, this is steam now, but it's starting at 100 degrees C. Okay, so the initial temperature for this calculation is 100 degrees C, and the final temperature is 120 in this problem. Okay? So let's see, let's do change in temperature over here. Change in temperature. Temperature final minus temperature initial. Now, after you write the equation up here, I really don't care that you write it a second time down here, but it never hurts. Okay? If you're doing 3 of these equations, and as long as you have this equation written up here, it's not such a big deal that you don't have change in temperature down here as long as you show me the math. So our final temperature is 120 degrees C. Our initial temperature for steam is 100 degrees C because steam can't be cooler than 100 degrees C. We have to start at 100 degrees C. So that's a 20 degree change. Okay? So 100 or 10 grams is our mass. We need to find a specific heat for steam. On your test references it says that gaseous water, which is steam, has a specific heat, or to be more correct, it's the well, it says specific heat here, but specific heat is the same thing as heat capacity. When I use CP, that actually stands for heat capacity, okay? And so we're using this equation here. Let's make sure we write it down here. Mass times specific heat times change in temperature. That's what we're plugging in for. And our specific heat or heat capacity for steam is 2.02 joules per degree C per gram. So that's a wrong number right there. Make sure if you haven't changed it on your references, you do so now. Okay? I got to get that fixed on that in the future. So 2.02 joules per degree C per gram. Put that over 1, and then we've got a change in temperature of 20 degrees. Cancel out grams, cancel out degrees C. We're ready to go to the calculator. So we've got 10.00 times 2.02 times 20.0. So that's 404 joules. And we need 3 significant digits, so we don't have to do any rounding here. But now we need the total Q. Okay? Total Q is the sum of all the parts. Okay? And I don't know, how many of you have taken calculus before? No? Okay, then I'll just write sum of all Q's. How about that? Is that good enough for you? That makes sense to you? So the Q total, sum of all the Q's, and that's going to be this Q, 2.09 times 10 to the third joules, plus 2.26 joules, plus 404 joules. Okay? So we've got our answer down here in scientific notation in two places. How are we going to add these up? Okay? In order to keep up with significant digits the way we need to. Okay? So here's what I'm going to do. I want to say 209, and then since I need 3 digits, I want to put an arrow right here in the place of my 0. That makes sense? So up here, before we rounded it off, we had a 0 there. I took it out and left an arrow there just to keep up with it for the addition. That makes sense? Okay? And then the second number here is 2.26 times 10 to the fourth. Well, that started out as that number. We rounded off these 2 digits. So I can do 226 and put 2 little arrows here just to kind of keep up with those places. Does that make sense? Okay, and then I can put down 404. Okay, there's a lot of ways to do this so that it works out, but I want you to keep up with the significant digits and know how to do it, and do it well. All right, so we add all those together, get a 4 here, 9 here, 10 here, carry 1, that's a 5, and a 2. Okay, but we've got empty slots above these last 2 digits. That means these last 2 digits have to be rounded off. We have to have units of measurement for any number. Okay? If you don't have the units of measurement, it's not true. Okay? That makes sense? A number without a unit of measurement, and if necessary without a species that goes along with it, doesn't tell you anything really. It's just theoretical. Put the units of measurement and the species where it's required. Okay? Yes? Yeah. Yeah. Now, later on in classes after this one, go to college or whatever, you could probably add these up in your calculator and figure out in your head how many significant digits you need. Okay? But do it on paper for me so you get in the habit of writing it down and visually seeing yourself doing it. Okay? So you're getting 2 different kinds of input. You're getting kinetic input from writing it down. You're getting visual input from looking at it. Okay? And then you can see more clearly what it is you're supposed to do. After you practice this stuff over and over again in this class, then, rounding off properly in college will be easy maybe, I hope. All right? Anyway, let's round off now. And we get our final Q of 251 joules, right? Now, 2.51 times 10 to the 4th power joules. Okay? Does that make sense? And that's our QT. And y'all thought that was a convenience store, didn't you? Huh? There you go. Good workout. Good mental workout. Look, I have students sometimes tell me, Mr. Taylor, these problems give me a headache. You know what?
No, I like that.
You know what? If you're working out with your muscles, how do you feel after a good workout?
Tired.
You're tired and sore, don't you?
Yeah.
Okay.
It's not good to feel tired and sore after the first walk when you have so many other ones.
Well, the way that you get your brain working sometimes leaves you a little bit of a headache until you get flexible with your brain. Okay? Until you build up that sort of flexibility and that ability to be able to tolerate this amount of using your brain. And you're at a point in your life where your brain is changing. Okay? Your brain is changing, and this is the point where you need to start this problem-solving skill. Okay? And actually put it into practice. And it's going to help you a lot. If you don't get in the habit of problem solving now, when you're 25, you're going to have a tough time problem solving. So if you get in the habit of problem solving now, this tough kind of problem solving, it's going to make your life easier later. What do you got to solve when you're 25? Oh, just wait. Just come back when you're 25 and and
Okay,
and,
but give me
and ask me that question.
Give me an example, Mr. Taylor.
There's life.
I'm gonna have to solve it like this.
I don't know, but problem solving is problem solving, whereas this problem solving other kinds. Okay? Working out your brain now is just like working out your body now. Okay? In a sense. Yes.
How do you, why do you have to put it in scientific notation?
Okay. You have to put it in scientific notation because we're getting rid of a digit in the ones place. That's the simple answer that I always give. Anytime you have to round off a digit in the ones place, your answer must be written in scientific notation. Okay? There's a more complete answer than that. It's just more complex and unnecessary at this point.
What if you have like 0.05?
0.05, that doesn't have to be written in scientific notation. Yeah. Because you're not getting rid of a digit in the ones place. So technically, any number that already has decimal places doesn't have to be written in scientific notation. Sometimes it's very convenient to do that, though. Okay?
So what if it has like 0.05 at the end of that? You wouldn't do it?
Oh, if I have to round off the digits over there, yes. The key thing is look at that that single digit position right here, okay? A ones place digit. If I've got to round that off, then you've got to write it in scientific notation. Okay? It's a requirement in this class. All right? Questions? Any other questions? Yes.
For the last one, the exponent on there, you got that based off of just the highest one?
No, I got it because I had to move the decimal place from here, okay, because this is in the ones place and there's a tenths place over here. The decimal place is right here, 1, 2, 3, 4 places. Okay, so there's 10 to the 4th. All right, anything else?
Can we get another one?
We don't have time to do another one of these because we've got to get ready for a test and we've got to save some room for other questions, okay? So in this problem, we've got 25 moles of butane 1-all. That's our standalone amount. Butane, 25.00 moles of butane 1-all. And we're going to put that over 1 because that's our standalone amount. That's our starting amount. Okay? We want to convert that amount into energy. It's asking how much energy is released. So to do that, we need this value, the change in enthalpy value for this equation. Okay? When we burn this stuff right here, butane 1-all, with oxygen, we get CO2 and water. We also get this amount of energy leaving the system. Well, what we're looking for is what is happening, what is being released here. Bye now. What's being released here is the energy that leaves the system. This is what's happening inside the system. What we want is the energy released from the system and to the surroundings. Okay? So that's not a negative 2874 because that's what's happening inside the system. What we want is positive 2874 kilojoules because that's what's happening in the surroundings. Okay, now when we have just the word mole on the bottom, that means 1 mole. And what is that mole applying to? The species here is butane 1-all. We're going to write that down here. Okay. And we can cancel units, cancel species, and do the math to find the amount of energy released. So let's see, 25.00 times 2874, and we get this number. Okay. And what we have here are kilojoules left. Yes, what's your question?
2874 is the combustion of actual butane.
Yes.
I thought it was butane 1-all was 2671.
Did I write the wrong number down here?
I thought that's like regular butane, but the thing that's butane 1-all.
Well, this is butane 1-all. Same formula here and here. And so when we write it like this, with delta H over here to the right, that just means that's the energy released from 1 mole of this chemical species.
So you can change the amount of energy released then? So you
No, you can't change the amount of energy released for a particular species, but this is not butane now. This is butane 1-all.
Yeah.
You
Butane
didn't
one
want
all
all
is 2671. Yeah, 2671. Not 2874. That's butane.
So you're telling me on the references I just wrote down the wrong number?
Yeah.
Well, you use what I put down here in this case, okay? You're right. I should have a different number there, okay? Fair enough? All right. How many significant digits do we need to keep?
No.
4. Zeros, when there's a decimal place, trailing zeros are significant. So this is 1, 2, 3, 4 digits. This is 4 digits that are significant. We need to have 1, 2, 3, 4. Underline this digit right here. That's the one we want to get rid of. We're going to move our decimal place 1, 2, 3, 4 places to the left. So we get 7.185 times 10 to the 4th power kilojoules. Does that make sense? So if we have a problem like this, we're going to look first of all at the species we're looking at. Water's what we're dealing with here, okay? And this heating curve graph is for water, all right? And then we look at the temperature range from 85 to 22. Well, 85 to 22, that's between here and here. So if we move over here, well, that must be this curve, part of the curve right here, okay? So this is the range we're talking about here. And this is the equation we're talking about. Anytime you're changing temperature, and this is talking about changing temperature, you need the equation that has the change in temperature term in it. Okay, so Q is the energy or heat energy, M is mass, specific heat or heat capacity here, that's listed for you, and change in temperature. Yeah. Now, what you should do to solve this problem is to make a list of what you know first. All right, so if we look at the problem, we can see that the mass, M, is 47.33 grams. Okay? The specific heat or heat capacity is here for you already. Okay, I'm not going to write it down again. We do have a beginning temperature and ending temperature. Okay? So the beginning temperature we call initial temperature, or T sub I. So the beginning temperature is 85.5 degrees C. And the temperature that we end up at, where we're going to, is the final temperature, and that's 22.3 degrees C. So we've got a list of what we have in the problem. And it's asking for the amount of energy. Well, if we're going to find energy for a change in temperature, that's Q. And you look over on the graph and you find the right equation to fit there. Okay? So for this calculation, where we're changing temperature from one temperature to another, we've got to have a change in temperature term. And the equation that has change in temperature is the same, whether it's solid or liquid or over here for gas. All three of those are the same equation. You have to plug in a different specific heat or heat capacity. Okay? So the equation we're going to be using then is mass times heat capacity or specific heat times the change in temperature. So what is change in temperature? Well, that's an equation you need to know. You need to memorize that change in temperature is always temperature final minus temperature initial. Final temperature minus beginning temperature. Okay? I've taught you that if you're going to add or subtract, you need to do that vertically so you can keep up with significant digits. So let's find the final temperature. Which one of these two right here is the final temperature? We've already labeled it. It kind of makes it easier. We don't have to go back to the problem now and figure out what the final temperature is. Yeah, so we're going to start with 22.3 on the top. All right. And since we've already done the work to figure out what final and initial temperatures are, we know that the initial temperature, which we subtract, is right here. So we're going to subtract 85.5 degrees C. And so organizing like this helps us in the problem solving because it means we don't have to do as much figuring out at the point where we're trying to figure out how to set up the math. We can figure out one thing at a time. Okay, so if you organize, it'll help you to figure out how to solve the problem a lot easier. Okay, don't try to save on pencil graphite because that just makes your life harder, really, in the long run. Okay, so now we need to subtract this number from that number, and you need a calculator for that. I mean, you can do this without a calculator, but it certainly helps to make sure you get the right answer. All right, now make sure that you come with a calculator tomorrow. Okay? You're supposed to have a calculator in this class. It's one of the required supplies. Make sure you bring your scientific calculator tomorrow. What do you call expensive? It's not $100 to buy a scientific calculator.
How much would you do?
$11.
$11?
Yeah.
Where?
Well,
Any department store or office supply
Name
store.
it. I don't, you gonna tell me where.
$11.
I'm not going to name the store. Either one. All right. So we have what we need to plug in and find the answer. Okay? Mass is 47.33 grams. We just plug that in. There's the mass term right there. We plug in the number, 47.33. What's your question? What's your question? All right, so the specific heat I gave you. All right, you can find it on the test references. The test references have the specific heat of liquid water listed right here. Same number. Okay, and then the change of temperature we calculated here to be negative 63.2 degrees C. Now I'm putting both this term and that term over 1 because it's keeping things organized. The same reason we wrote down what we knew up here. It keeps it organized and makes it easier to figure out the problem. Less to have to run through your head when you've got it written down. Okay? Now we can simplify. Grams can cancel because I've got a gram on the top and a gram on the bottom. Units of measurement can cancel each other, just like X's and Y's in algebra. Degrees C can cancel. Those are units of measurement. And so we've canceled everything in here except this unit of measurement right here. And joules is a unit of measurement that measures energy, and Q is for heat energy. So we're looking for heat energy in the problem. Q is the heat energy, and joules measures heat energy. So we're set. You know, we probably set it up right. Now we need to make sure we use the right negative here. This negative right here means subtract. This negative means change of sign. Different calculators have different symbols for change of sign. I'll show you a couple of those in just a minute. Let me do the math first here. So I'm going to put it in parentheses just to make sure I'm separating the terms. What? Okay. There you go. So we get that number. The units of measurement we have left are joules. Okay? And we're going to have to round off to find the right number of significant digits and round off our final answer to the correct number. What you're going to look for are the measured and calculated numbers in the problem. Okay? For a multiplication division problem like this, you look at the measured and calculated numbers. Well, this is a measured number, and both these are calculated numbers. And this one has 4 significant digits, this one has 3, and this one has 3. And you want your final answer to have the number of digits that your least digits in the problem had. Okay, the measured or calculated number with the least digits is going to govern how many digits you keep in your final answer. So starting from the left, we count 1, 2, 3, and those are our significant digits. And everything else we underline to show they're insignificant. It's required that you underline. Okay? Draw an arrow. It's required that you draw an arrow to show that you're rounding off. Now, anytime you get rid of a digit like this 3 here that's in the ones place, we're going to have to round it off. So we're getting rid of a digit in the ones place. We have to write the answer in scientific notation. So we move the decimal place to between the first and second significant digit. So this is the first significant digit. This is the second. Move it over there between those two. 1, 2, 3, 4 places. And so the answer we're going to write is 1.25 times 10 to the, and since I moved it 1, 2, 3, 4 places, it's 10 to the 4th power joules. And that's how you find the answer. Alright, so we set on my calculator that this button right here was the change of sign button. Different calculators have different symbols. This calculator has a change of sign button that looks like this. This is the subtraction sign. That's where you subtract. This is where you change the sign of a number. Okay? Let's see what else I have in here. Anything that's different. That one's got the same kind of change of sign button. Okay, this one's got this kind of change of sign button. So you have to know what's the subtraction button on your calculator right here and what's the change of sign button. Know which one you're using. Okay? So the negative needs to go here to show that's a negative number. I just failed to move it over a moment ago. But that's a negative number, so when I round it off, it's still a negative number. So when you're talking about the energy in the system being changed over the course of some kind of reaction, you're looking at a graph that we call a reaction energy diagram. Okay? That's up to you. Somebody asked me to go over this. Okay, I'm just saying I'm going over it because I was asked about it. Okay? Now, what this is showing is how the reaction changing, okay, how the course of the reaction affects the energy in the system, and that's delta H. If it's energy in the system, that's delta H, okay? So you can say progress of the reaction if you want to. Okay, you could put reactants over here and products over here and draw an arrow between them because progress of the reaction means we're going from reactant to product. It kind of means the same thing. Okay? And so the progress of the reaction, there's always some kind of energy change in any chemical reaction. Sometimes the change is not enough to really notice, but it's there. Okay? And so what we're looking at with these is the change in enthalpy in the system, which we symbolize as delta H. We use H because it used to mean heat, and as science developed, we found out there's other kinds of energy besides heat, so we call it enthalpy now. But it's the change in stored energy in the system. At least that's what we use, that's what we call it in high school. It's more than that, but for high school, we simplify it down to saying delta H is the stored energy in the system. So a reaction energy diagram for an exothermic reaction means that you start high and end low, because the system's losing energy, and that energy is being moved to where you are. It's being moved out from the system, and it might feel warm or hot or something, okay? So if you're losing energy in the system, it's going to the surroundings where you are, and that's why it goes down in the system. That's what delta H is about.
But I thought it was the other way, like, you know, oh, never mind.
There's an endothermic reaction. We'll do that one next.
Is that one with temperature?
No.
Oh.
We're not looking at the temperature for a reaction energy diagram. We're looking at what's happening with the energy that's stored in the system. Okay? It affects temperature. We're not looking at it with this graph.
It's usually during the what? Endothermic? Yeah.
Endothermic doesn't look at temperature change either.
No, I'm
Oh.
saying you would be going up like. from
Yeah.
the-
Endothermic would start low and end high.
Okay.
So you still got to have this hill here, okay? And that's the activation energy. The difference in the amount of energy you start with and the amount of energy in the system you end with here, this difference here, we're losing energy in the system. That's the actual change in enthalpy, okay? The difference between the energy you start with and the amount of energy you've got to add to get the reaction moving, that's called the activation energy. Now, if you guys are getting ready for the test, and we are because we have a test tomorrow, writing it down a second or third time probably helps you to remember it so that you'll do well on the test. Okay, so sitting back and just waiting on me to tell you or texting on your phone isn't getting it done. And if you're not preparing for success, you are preparing for failure.
Not necessarily.
So this is activation energy. And so this is for an exothermic reaction. Now, if we want to look at what's happening with a catalyst, and a catalyst just reduces the amount of activation energy required. A lot of times we think about catalysts speeding up reactions, and they have the effect of doing that, but the reason they do is this is the slow part of the reaction. Think about a roller coaster. What's the slow part of the roller coaster? When you're going up that first hill, right? Well, this is like that first hill right there. It's slow going up. If I want to get over that hill faster, I either got to push it a lot faster, crank the engine up or pull the chain faster or something. But I could create a roller coaster with a smaller hill, and I'd go over it faster. Okay? So if I want to make the reaction move faster from this side to this side, I can shut that or shut that off or shave it off. And that's what a catalyst does, okay? It shaves off the top or cuts down the top of the energy hill so it's not as hard to move the reaction forward to get it going. Okay? All right, so let's look at the same thing then in the case of an endothermic reaction, okay? So up down here we're going to have a reaction energy diagram. For an endothermic reaction. And then we'll add the catalyst in there in a minute. Again, we're going to have progress of the reaction at the bottom, or as I said, you can say reactants on this side and products on this side, if that's the way you prefer to label it. Okay, we're going to have the change in enthalpy or the change in stored energy in the system over here. Now in an exothermic reaction, you started high and ended low. because you're reducing the amount of energy in the system, and that energy is being delivered to where the surroundings are, where you are, and it's going to feel warm. But with an endothermic reaction, instead of delivering energy to the surroundings, we're taking energy from the surroundings and putting it into the system, into the chemicals that are reacting. And so we're going to start low and end high. And the reason that a lot of endothermic reactions feel cool when you touch them, or when you have your hand near it or whatever, is because it's taking energy away from where you are, and you feel cool. Yes?
Which one is this one?
This is an endothermic reaction.
Can you go back up for a second?
Yeah. This is exothermic. Energy is being reduced. Now we have endothermic, where energy is being gained by the system. But we still have to have that activation energy. The difference between the energy that we started with and the energy we are ending with is still delta H, but this time it's going up. The change in enthalpy in the system, the energy being stored in the system, is increasing. You still have to have activation energy. The energy you start with compared to where you have to get to make it move forward, that's the activation energy. And if we want to see what happens with a catalyst, it works the same way. We're just going to cut off the top of that energy hill.